Okay, we should be very familiar with the idea of a Bronsted-Lowry, the Bronsted-Lowry definition of an acid as being proton donors. Okay, so but sometimes this isn't, you can't explain everything. So for example, and it's important when we're doing this, the oxides of period 3, to get this idea of a Lewis acid. Okay, so now we say carbon dioxide is an acidic gas. Sulfur dioxide is also an acidic gas. Sulfur trioxide is acidic. Well, obviously they can't be acids in the Bronsted-Lowry sense because they haven't got any hydrogen in them. There must be something else going on. Right, so there's a slightly modified definition of an acid, which we're going to use sometimes, a Lewis acid. And a Lewis acid is described as a lone pair acceptor. So a species which accepts a lone pair of electrons. Okay, so and the base would be something which gives away a Lewis base. It's a lone pair donor. So let's have a little think about ammonia, which we were familiar with it being a Bronsted-Lowry acid, a Bronsted-Lowry base, sorry. So here we've got NH3. Let's see how it reacts with water. Well, we have a lone pair on the nitrogen, and if we react that with water, what happens is that lone pair go onto the hydrogen there, and then this pair of electrons goes into the oxygen, so you'll form NH4 plus. And OH minus. Okay, so we've got no problem there with ammonia behaving as a Bronsted-Lowry base because it accepts this proton. Okay, but we can also say it acts as a Lewis base because it donates this proton. Okay, it donates a proton to the hydrogen atom, forming a dative bond. So just to show you that the two ideas are not contradictory, just different ways of looking at the same thing. Okay, so let's try and think about carbon dioxide then. We say carbon dioxide is an acidic gas, but it can't be a Bronsted-Lowry acid. So if we look at the bonding with carbon dioxide, right, it's like that. And when you get carbon dioxide and dissolve it in water, you end up with a solution of carbonic acid, which is a weak acid, very weak acid, but it's acidic and give the water pH 5, something like that. Rainwater will have a pH of about 5. All right, let's see how that's going to react with water. So we've got a water molecule here. Right, 2 lone pairs on the oxygen. Right, we know that carbon is going to be fairly delta positive because it's connected to 2 electronegative oxygen atoms. So that means that this one of these lone pairs is going to be attracted to the carbon. Okay, and the carbon can accept that lone pair. So this lone pair is going to move onto there, and it can do that because it can break one of the pi bonds. Okay, so we can see here the water, what's it done? It's donated a lone pair. So that's acting as a Lewis base. Whereas the carbon dioxide has accepted the lone pair, the carbon has accepted the lone pair, so that's the Lewis acid. Okay, and then let's just see what happens in there then. So you're going to end up with this intermediate. So you'll have an oxygen. Of course, there'll be a positive charge on that oxygen. And you'll have, this is the oxygen with the pi bonds broken. That will have a negative charge on that. So then that's going to, for that lone pair, that's obviously going to pick up that proton. And that's going to go back into there. So you end up with carbonic acid. And carbonic acid this is a Bronsted-Lowry acid because it's got 2 protons there which it can give away. Okay, you give both of those away to form the carbonate ion. So we can see there, we start off with CO2, which is a Lewis acid, and we end up with carbonic acid, H2CO3 here, which is a Bronsted-Lowry acid. And that's a kind of a familiar kind of pattern that happens. Let's see what happens with SO3, sulfur trioxide. It's extremely similar. Well, if you get SO3 and you react that with water, you form sulfuric acid, and sulfuric acid, of course, is a Bronsted-Lowry acid. Whereas the SO3 we'll see in a minute is a Lewis acid. So if I draw my sulfur trioxide here, right, and now that sulfur is going to be pretty delta positive. It will have a charge on it, partial charge, because it's connected to 3 electronegative oxygen atoms. Right, so if you add that to water, a very similar situation has happened with the carbon dioxide. The lone pair on the water is going to go there. So here's the water is donating a lone pair. So that's acting as a Lewis base, donating a lone pair. The sulfur trioxide is acting as the Lewis acid there. It's accepting that lone pair. And when it does that, one of these pi bonds is going to break. So you'll end up with okay, one of those is broken, so that's going to have a negative charge on it. And the water is now forming a dated bond there, so that will have a positive charge on the water. And then obviously that proton will be picked up by that oxygen, and we're going to form sulfuric acid, which is of course a Bronsted-Lowry acid, because we've got those 2 protons. They're both acidic, these protons, and they can lose them and form the sulfate ion, the SO42- ion. So once again, we start off with a Lewis acid, react it with water, and we end up getting a Bronsted-Lowry acid. And I'll just, before we finish up, I'll just remind you, if you've done transition metals already, how the hex aqua ions can behave as acids. So if we think of an anhydrous copper 2+ ion, right, that, if you add water, is going to form the hex aqua. And of course, those waters form dative bonds to the, they donate pairs of electrons to the central copper atom. So copper atom's accepting the electrons, so that's going to be a Lewis acid. The water's behaving as a Lewis base because that's giving away the lone pairs. And then if you've done this topic yet, you'll see that this is actually a Bronsted-Lowry acid because you have all those water molecules. Let's just think of, just draw one. That's forming a dative bond to the positive copper ion. That withdraws charge out of the water molecule, reduces electron density here, so it makes that proton, or one of those protons, acidic. So it is the copper hex aqua ion is a Bronsted-Lowry acid. So once again, Lewis acid, add water to it, and you end up with a Bronsted-Lowry acid. Okay,